application problems. So, of course, all of this math that we've been learning so far seems very theoretical and doesn't seem like there'd be many situations where we could apply this in. But actually, exponentials and logarithms are very useful in real life, and there's lots of situations. For example, a very relevant example that we've got right now is the growth of the coronavirus in amongst the world. So we can see that every day it is growing at a rate that creates a curve of this specific shape because it's growing so rapidly that it's at that number. We will get to a point though where it's going to start decreasing, and so it'll start resembling a log graph. So these types of growths or decays can be modeled. These types of growth or decay can be modeled on our logarithmic and exponential graphs. Our general form for our application problems is always going to look like this. So A is the amount that I have. A0 is my initial amount. The reason that this is our initial amount is because, and I'll explain in a moment why that is, we will generally use a base of 2. This base is just how long it takes for something to this base here is just the rate at which it grows every hour. So for example, if it doubles every hour, then it'll be a 2. If it triples every hour, then it'll be a 3. This k is our constant. We will always have a k value, so you will need to use some sort of information in the equation to be able to know, in the question to be able to find k. And finally, t is time. Now just back to this idea of why a0 is our initial growth. Well, initial means at the beginning. So when time is equal to 0, let's substitute it into this equation. K times 0 is just 0, and we know that anything to the power of 0 is 1. So what we'll get is that the amount when time is 0 is always a0. And that's why we don't have to do this working out. We can just plug in our initial value straight away into it. K is our growth constant. Now, there are some specific situations that results in a different type of constant. So, for example, the generation time, which is called TD, is where we have our power T, so our time, but it's divided by TD. So this is the generation time. So, for example, if it says that it will take 15 minutes to grow it will take 15 minutes for this much bacteria to grow, then our generation time will be inserted into there as 15. So here's an example that models this. What is the generation time? So how long does it take, really, of a bacterial growth? What is the generation time? So that's they're asking us to find the TD of a bacterial population that increases from 5,000 cells to 100,000 cells in 4 hours of growth. So this 5,000 cells is our initial amount of cells. So that's when time is 0. And if you remember, that also means that our A0 is 5,000. And they're asking us for 100,000 cells in 4 hours of growth. This tells us that at 4 hours, the amount of bacteria that I have is 100,000. So I can model my equation. It'll be A equals A0 times 2 to the power of T on TD, where TD is my generation time, and that's what I'm looking for. I can now substitute in my A0 because I know what it is initially. And now I can use this other point to help me find the unknown. Now, I can use this as 4 in terms of 4 hours, or because they're quite large numbers, I'm just going to change this into minutes, which is 240 minutes. So now I will substitute this into my equation in order to find TD. So that will be 100,000 is equal to 5,000 times 2 to the power of T on 240. I will divide both sides by 5,000. So 1, 2, 3, 1, 2, 3 leaves over 100 divided by 5. 100 divided by 5 is 20. And then to get this 2 to the other side, we just have to take the log. time is 240 over TD. I'm going to divide both sides by 5,000. Of course, because this is a worded problem, we generally will have our calculator with us, but just in case we don't, if we divide both sides by these 3 zeros, and then 100 divided by 5 is 20. So that'll be 20 equals 240 on TD. Then I can take the log of both sides. And then to get TD to the top, I just multiply it over and divide by log 240. So TD will equal 240 on log 2 of 20. This, of course, is a value that I can't work out in my head. I will need to use a calculator. Which is 55.53 hours or minutes. Another situation that we have is decay. So decay is used in situations such as being able to know how long a particular ancient material has been around for. There are certain elements, such as uranium, for example, that decay over time. And the way that we're able to test how long it's been there is through its half-life. So if we know what the half-life of a material is, then we're able to figure out, well, how much of it is left at the moment, therefore how long has it been around for. The half-life means that whatever the time is, that's how long it takes until the amount is half of what it originally had. This is my general equation for decay. Again, I've got a base of 2, but this time, because I am decaying, it is becoming less and less, my K is going to have a negative in front of it. After 1,000 years, a sample of radium-226 has decayed to 64.7 of its original mass. Find the half-life of radium. So after 1,000 years, so when time is equal to 1,000, the amount that I have is 64.7. Now 64.7 can be rewritten as 0.647 as a decimal of the original amount. And we know the original amount is always called A0. Find the half-life of radium. So what that's telling us is find the time for which the amount is 0.5 of the original. So again, if I have my equation A equals A0 times 2 to the power of negative KT, my first step is to find K, so that's always using a point that I know, and then my second step is to answer the question where I have that question mark. So step 1, let's find K by substituting in that point. So I have 0.647 A0, that's my amount, is equal to my initial times 2 to the power of negative K 1000. Even though I don't know on my initial, that's fine, because now all I need to do is divide both sides by that initial amount, whatever it is, and it actually ends up cancelling out. So it's not a problem that it's not there. Take the 2 over, I need to take the log of both sides. And then to get K by itself, I will divide both sides by negative 1000. Again, this is not a value that I can work out in my head, so I will need to refer to my CAS. and that'll equal 0.000628, so on. Now, what you might notice about this k value is it's incredibly small, and also I've missed out on a whole bunch of decimal places, which is really going to affect my answer. So that means when I actually use my k value in the next part, I'm not going to use that approximation here. I'm going to use the exact value, which is this here. And I'll show you what we mean by that. So we've now done part one. This one has helped us find k. We're now up to part two, where we're going to find the half-life. So the amount that I'm looking for is half of the original, equals the original times 2 to the power of. So instead of writing this whole decimal, I could write this fraction, but again, because this fraction is quite large, I'm just going to write k for now, but I know in my head I've already found it, and it's this fraction here. Divide both sides by a0, and then I can take the log of both sides. And then I can find t by dividing both sides by negative k. Now is the point where I can sub k back in. So I know it's log 2.5, and k, that's going to be divided by the answer that I found beforehand. So the answer that I found beforehand was this over here. So that will be divided by log 2.647 over negative 1000. And then this whole thing is what goes into your calculator. As you can see on my calculator here, that is equal to 1591. So I'll just transfer that over. So that's 1591 years. The last type of question that you might come across is exponential rules. Now, you've already done this in pretty much every exercise that you have had in the past to do with graphs. Basically, you've got a function that you've got unknowns in. For every unknown, you need a point. All you need to do is substitute it in and then solve. So we've got the points 1 and 6, 5 and 96 that are known to lie on the graph or on the curve y equals a times bx. So my two unknowns here are a and b, and that's quite nice because I have two points, which is 1 and 6 and 5 and 96. Find the values of a and b. Well, all I'm going to do is substitute each of these values in. So sub value 1 in, that's x there and that's y. So that'll be 6 equals a times b 1. That will be ab. And then for 2, that will be 96 equals a times 5x times b to the power of 5. So that'll be 96 equals a b5. There are several ways that you can go about solving this. One of the ways is through elimination. So what I can do is I can divide equation 2 by equation 1. So what that would look like is 96 equals a, b to the power of 5, and then divide each of these by its corresponding part. So 96 divided by 6 is 16. The a's cancel out, and I've got one b there. I will have 4 b's left over. I can rewrite 16 as 2 to the power of 4, and so since the powers match, b will equal to 2. Once I find that, I can now substitute b in. Sub b into, doesn't really matter which equation, one is probably easier. to avoid the large power. So that will be 6 is equal to a times 2, and then divide both sides by 2, I will get 3. So there's my answer there. And now I can rewrite the full equation. Y is equal to 3 times 2 to the power of x. And that is my final equation.